Finding roots of complicated equations is very difficult and sometimes impossible, so we are forced to use graphical methods. We use graphical methods to approximate the root by performing a defined set of calculations over multiple iterations. This means that we approximate more accurately and get closer to the actual root with each iterations. Hi everyone, my name is Ingrid Tiaranwari, and in this video we're going to walk through solving a problem using the bisection, false position, and also the Newton-Raphson method in Google Colab using the Python programming. So our problem states to find root with the function of minus 6x cubed plus 6 plus 2 using all the three methods I mentioned. As for the first one, we're using the bisection method, which is one of the simplest, reliable, easy to implement, and convergence guaranteed method for finding real root of nonlinear equations. It is also known as binary search or half interval or Bolzano method. The bisection method is a bracketing method and starts with two initial guesses, say x0 and x1, such that x0 and x1 brackets the root. An example, f of x0 times f of x1 is less than 0. Bisection method is based on the fact that if f of x is real and continuous function, and for the two initial guesses, x0 and x1 brackets the root such that f of x0 times f of x1 is less than 0, then there exists at least one root between x0 and x1. Root is obtained in bisection method by successive halving the interval. In example, if x0 and x1 are two guesses, then we compute new approximate root as x2 equals to x0 plus x1 divided by 2. And now we have three different cases. The first one, if f of x2 is equals to 0, then the root is x2. The second one, if f of x0 times f of x2 is less than 0, then root lies between x0 and x2. The third one is, if f of x0 times f of x2 is more than 0, then the root lies between x1 and x2. And then the process is repeated until we find root within desired accuracy. As for the bisection method algorithm stepwise, firstly, we're starting by defining the function of fx. Then we chose initial guess x0 and x1 such that f of x0 times f of x1 is less than 0. Then chose a pre-specified tolerable error e. After that, calculate new approximated root as x2 equals to x0 plus x1 divided by 2. Then calculate f of x0 times f of x2. If f of x2 absolute is more than e, then go to step 5. Otherwise, go to step 8, which is display x2 as the root. The rate of convergence of the bisection method is linear and slow, but it is guaranteed to converge if the function is real and continuous in an interval bounded by a given two initial guess. The accuracy of bisection method is very good, and this method is more reliable than other open methods like the second method or the Newton-Raphson method, etc. Despite being slower to converge, the accuracy of this method increases as the number of iterations increases. In bisection method, error is reduced by factor of half after each iterations. So we can write en plus 1 divided by en equals to half, which gives en plus 1 equals to 0.5 en. Here en plus 1 is error at n plus 1th iteration and en is error at nth iteration. From equation, it can be concluded that error at n plus 1th iteration is linearly related to error at nth iteration. For this reason, bisection method is said to have linear rate of convergence. Now for the second method, we're using the regular false, also known as false position method, which is one of bracketing and convergence guaranteed method for finding real root of nonlinear equations. False position method is bracketing method, which means it starts with two initial guesses, say x0 and x1, such that x0 and x1 brackets the root. In example, f of x0 times f of x1 is less than 0. Regular false is based on the fact that if f of x is real and continuous function, and for two initial guesses, x0 and x1 brackets the root such that f of x0 times f of x1 is less than 0, then there exists at least one root between x0 and x1. If x0 and x1 are two guesses, then we compute new approximated root as x2 equals to x0 subtracted by x0 minus x1 times f of x0 divided by f of x0 minus f of x1. And now we have three different cases. The first one, if f of x2 is equals to 0, then the root is x2. The second one, if f of x0 times f of x2 is less than 0, then root lies between x0 and x2. The third one is, if f of x0 times f of x2 is more than 0, then the root lies between x1 and x2. And then the process is repeated until we find root within desired accuracy. As for the false position method algorithm stepwise, we're starting by defining the function of fx. Then we chose initial guess x0 and x1 such that f of x0 times f of x1 is less than 0. Then chose a pre-specified tolerable error e. After that, calculate new approximated root as x2 equals to x0 subtracted by x0 minus x1 times f of x0 divided by f of x0 minus f of x1. Then calculate f of x0 times f of x2. If f of x2 absolute is more than e, then go to step 5. Otherwise, go to step 8, which is display x2 as a root. The false position method is a very old and still used approach to solve equations with a single unknown in mathematics. The regular false method of the known has an order of convergence greater than 1. It is a traditional approach to solve one-variable equations in mathematics using false or test value for the variable and then changing the test value in response to the outcome is how the method is best expressed in plain English. When we compare the power of the two sides, we have p equals to 1 plus 1 over p, which resulted in p equals to 1 root 5. By ignoring the negative sign, we arrive at p equals to 1.618 as the convergence rate. This method is the oldest method for computing the real roots of an algebraic equations. A nonlinear equation of form fx equals to 0 can have roots using an iterative process called the false position method. With the use of this technique, we can more accurately estimate the equation's root. It is a traditional method or approach to solve one-variable equations in mathematics. For the third method, we're using the Newton-Raphson method, which is an open method and starts with one initial guess for finding real root of nonlinear equations. In Newton-Raphson method, if x0 is initial guess, then next approximated root x1 is obtained by the following formula, which is x1 equals to x0 subtracted by f of x0 divided by fa of x0. In this case, fa is a derivative from f. And an algorithm for Newton-Raphson method involves repetition of above process and example. We use x1 to find x2 and so on until we find a root within desired accuracy. An algorithm for Newton-Raphson method requires following steps in order to solve any nonlinear equation with the help of computational tools. We're starting by defining the function as f of x. Then define the first derivative of f of x as g of x. After that, input the initial guess of x0, tolerable error e, and maximum iteration n. Then initialize iteration counter I equals to 1. If g of x0 equals to 0, then print mathematical error and go to step 12. Otherwise, go to step 7, which is calculate x1 equals to x0 subtracted by f of x0 divided by g of x0. Increment iteration counter I equals to I plus 1. If I is more or equals to n, then print not convergent and go to step 12. Otherwise, go to step 10, which is if f of x1 absolute is more than e, then set x0 equals to x1 and go to step 6. Otherwise, go to step 11, which is printed as x1. To reiterate, Newton's fixed point theorem tells us that the fixed points of the function n of x are the roots of f of x. Furthermore, because the roots of f of x are attracting fixed points for n of x, as we iterate n of x, the resulting sequence of the points will converge to the root of f of x. As you can see here, this is how I compute in Google Colab using the Python program to find the roots of the equation minus 6x cubed plus 6 plus 2 using the bisection method. Using the false position method, using the Newton-Raphson method. Alright everyone, that's all from me on how to solve a problem using the bisection, false position, and also the Newton-Raphson method in Google Colab using the Python programming. I hope you find this video insightful, and also last but not least, I humbly thank you very much for your time and attention. See you next time. Bye.